In this video, I'll demonstrate how to prepare a dataset before creating a linear regression model. So on line 1 of this example code, I bring in the dplyr library because we're going to use a few of its functions in this demo. So I'll call library dplyr to load the library, and then I call the dplyr glimpse function to look at the dataset we're going to be working with. And this is the built-in air quality dataset. So this air quality dataset contains 153 observations and 6 variables. And those variables are ozone, solar.r, wind, temp, month, and day. But this doesn't tell us a whole lot about what this data set is. Now, we know what the variables are and know what the observations are, and we have the types, so int, int, double, int, 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 and some of the values. But what are we working with? Well, this is a built-in data set, so we can call help of air quality, and it will load the R documentation for this data set. So these are New York air quality measurements. These are daily measurements from New York from May to September 1973. So what this is showing is the ozone in parts per billion, the solar radiation in Langleys, wind in miles per hour, the temperature in degrees Fahrenheit, and the month and day that they were recorded. So the month will be a number from 1 to 12, and the day will be a day of the month from 1 to 31. Now what I'd like to look at is the relationship between wind and ozone. So does the wind speed have any effect on the ozone's parts per billion? Well, before we start to look at a relationship, we need to clean up the data. So we need to prepare the data. So the first thing I'm going to do is look for NA values. So on line 6, I call any NA of air quality, and that returns true. Well, the columns or the data points that I'm concerned about are the ozone and wind columns. Now, are there any NA values in those columns? Well, on line 7, I call any NA of air quality $ ozone, and that returns true. So we're going to need to filter those out. On line 8, I call any NA of air quality wind, and that returns false. So the wind values are fine. So now on line 10, I create a new data frame, a dplyr tibble called air, and I assign that to air quality. I use the dplyr pipe operator, so % greater than %, and I pipe our air quality data frame into the filter function. And to the filter function, I pass is.na ozone equals false. So I'm comparing that the is.na of ozone to false. So if we get anything other than an NA value, then we want to keep that record and include it in our air data frame. So we drop any records where the ozone is NA. So I'll execute lines 10 and 11 and create that new data set called air. And this has 116 observations of 6 variables. So there's still a fair bit of data to work with. And now as a sanity check, we can take any NA of air $ozone. Now remember, from this point on, we're working with the air data frame and not air quality. So any NA of air $zone is false, and any NA of air $wind is still false. So we have a data set that's ready for the next steps. Now, one thing we can do when we're preparing the data is get a sense of some values by using the summary function. So on line 16, I have summary of air $ozone, and that gives me the minimum value, so 1 part per billion, the first quartile, the median, the mean, the third quartile, and the maximum, which is 168 parts per billion, of our ozone data. And we can do the same thing with wind as I do on line 17. So I have summary of air $wind, and that gives me a sense of what I'm working with the wind variable. So we have a minimum value of 2.3 miles per hour, a maximum of 20.7, and a mean of 9.862. So this gets us to a point where we can start looking at the relationship between wind and ozone and create a model of it. And that's covered in the video titled Creating Linear Models. And that concludes this demonstration of some important first steps in data preparation before creating a linear model. In this video, I'll demonstrate how to create a linear regression model using the LM method in R. Now I've already loaded the dplyr library and filtered the air quality data frame as shown in the video titled Linear Data Preparation. So we're working with the filtered variant called air. The first thing we'll do is get some sense of the correlation between the ozone and wind measurements in our dataset. So we're looking for a relationship between wind and ozone. So for that, I'm going to use the built-in core function in R. So on line 6, I call core with air $ozone and air $wind as its arguments. And this gives us a result of negative 0.6015465. So it's roughly negative 0.6. Now what this says is there's a negative relationship between wind and ozone. So as the wind increases, the ozone decreases. So that's what the negative tells us. The 0.6 tells us there's a moderately strong correlation. So if the value was 0, there'd be no correlation. If the value was 1, there'd be a perfect correlation. So every increase in wind would be an increase in ozone, and if we drew a straight line through the points plotted by those, then they would all fall on that line. But negative 0.6 is still a strong correlation. Now, to get some sense of this, we can get a sense visually by plotting wind as a function of ozone. So on line 8, I plot ozone tilde wind. So this is plotting ozone as a function of wind, and the second argument we pass the dataset we're getting these variables from, the air dataset. And in the plot, we have our wind on the horizontal axis and ozone on the vertical axis. So if we get a sense of our points, as the wind speed is lower, the ozone appears to be generally higher. But as the wind speed increases, the points of ozone generally trend lower. Now you can see this, you could draw a triangle in the upper right-hand corner where there are no records of ozone in that range. As well, in the lower left-hand corner, we could draw a triangle there where there are no points in that corner. So there is a correlation. It does match what we'd seen in the core function, that we have a moderately strong relationship. So you can draw a line through these points and they're not randomly distributed. Now, one way we can see this a little bit more is if we plot a mean line of our ozone through this plot. So on line 9, I create a variable called avg underscore ozone for average ozone, and I assign that to the mean of air $ozone. So that gives me a result, a value for the mean ozone. And then if I plot this line using AB line, I specify the H equals average ozone, the H for horizontal line. And when we execute that, we get a line in our plot at the point about 42.129. So that's what we get in our avg underscore ozone variable. And that horizontal line is drawn through the plot. And you can see below about 6 miles per hour of wind, there are no points of ozone. And above 15 miles per hour, there are no ozone points there. It all falls below. So you can get a sense of the trend line. At this point, we can create our model. So I'm going to call the model ozone underscore wind, and I'm going to assign that to the LM function. And that LM function is defined in the same way we define this plot. So we have ozone tilde wind, or ozone as a function of wind, from the air dataset. So I'll execute line 12. And now I'll draw another AB line using that model. So this will plot the ozone wind result onto our graph. And you can see the line of best fit that the LM function came up with is drawn through our plot. So it's a decreasing line as we expected, because it's a negative relationship as we'd seen in the core function as a negative value, and it generally fits through the middle of our points. Now, if we'd like to see what the ozone wind model contains, we can just execute that as I've done on line 14. So I just specify ozone underscore wind. And in the console, we get two pieces of information. We get the call, so the formula used, so LM of formula ozone tilde wind and data equals air, and then the coefficients that define the line. So the intercept, 96.873. So at a wind speed of 0, the line starts at 96.873, and for each unit of wind, our ozone decreases by negative 5.551. So now we've created a model, and we have some informal sense of the relationship. And now we can look at the results in more detail and that's covered in the video titled Interpreting Model Output. And that concludes this demonstration of creating a linear model. In this video, I'll demonstrate some of the tools used to extract statistical results of a linear regression problem. So we start by setting up the data and the model and the plots we had in the videos titled Linear Data Preparation and Creating Linear Models. This is done on lines 1 to 8 of the example code. So once we have the results from the previous demonstrations, we can consider the tools we can use to analyze the results. Now first, visually, given the scatter plot and the line through it, on intuition alone, we can see some deficiencies in the model. So if we look at the maximum value where the wind speed is 0, the ozone is just under 100. But we have a number of values between the wind speed of 0 and a wind speed of about 5 or 6 that are above 100. So these points won't be modeled accurately. Then for very high wind speeds, so wind speeds over 15, our regression line passes under all of the points up until about a value of an 18 miles per hour wind. Then above this point, our regression line would actually dip below the 0 point. So we wouldn't be able to model any points of ozone above 18 because we'd get a negative ozone, and that's impossible. So we can see this visually from our graph, but we also want some numerical evidence of these limitations of the model. So where do we get our statistical information regarding the model? So if we output the ozone wind, then we get the formula that we called, so the LM formula equals ozone tilde wind, data equals air, and the coefficients. So the intercept where the wind is 0 is 96.87, and then for each unit of wind, the ozone decreases by negative 5.551. If we create a summary and then output the summary, we get all the important statistical information regarding the model. So in the summary, R provides, we can get our residuals, so the min, first quartile, median, third quartile, and max, the coefficients, including the standard errors, the t-values, the p-values, our coefficient of determination, the R squared, and the f-test values, so we can determine the statistical significance. We can also get all of the names of the ozone wind summary, so the summary names, so we can access these individually. We can call a glimpse on the summary to get more details about the structure of the summary if we want to extract particular values. So if we'd like to get the coefficients, on line 15, I call ozone wind summary $coefficients, and that just extracts the coefficients section, and we can actually index the coefficients by the row names and column names. So I can access ozone wind summary $coefficients, and then I specify the indices, the character string wind, which corresponds to the wind in the output, and the p-value, the PR, in parentheses greater than absolute t, so we specify this character string as the column name for the second variable. So if we execute this, we get the 9.271974 to the exponent negative 13. R also gives us a function vcov, that will generate the variance-covariance matrix for this model, and the conf_int for the confidence interval for this model. At this point, we can accept the model and use it to predict, which can be seen in the video titled Using Linear Prediction. Otherwise, we can attempt to adjust the model, possibly use a different method of modeling until we achieve a better result based on the summary information. And that concludes this demonstration of extracting the results of a linear regression model. In this video, I'll demonstrate how to use the predict method on a linear model. The model I'll be using comes from the progression through the videos Linear Data Preparation, Creating Linear Models, and Interpreting Model Output, which also covers the first 8 lines of this video in this example code. So I've already covered the code from previous videos and loaded it into this environment. Now, what we ended up with from those videos is not a great model, but it doesn't affect the predict method. But we have to be careful with the results and be aware of its deficiencies going in. Now, our models will never be perfect in general. There's always a trade-off. But I'd argue that it's more important to recognize where a model doesn't always fit well, like in this example, before correcting it or changing it, either by changing assumptions about the relationship between predictor and response, gathering more data, or changing the modeling method used, or a combination of all of these. In any case, the predict method is the same whether or not our model is good. So let's look at the examples. Now, the first example, on line 10, I have wind_data assigned to data.frame, and I set the wind variable to the vector created by the function c with the values 7, 10, and 12. So this will load the values that I'm going to use for prediction. So I'm going to use these values of wind to predict ozone. Now, if we consider the plot that we have and the values of wind between about 7 and 12, those values are reasonably well correlated with the ozone. Where the problems really occur is for wind speeds less than 5 or wind speeds greater than 15. So predicting on values 7, 10, and 12, our model should do a reasonably good job. So on line 13, I have wind_data, and I create a new column, so I index our wind data with a character string ozone prediction. So I'm going to store the results of the prediction in this data frame as a new column. So I assign this to predict, and the first argument is the model, which I've called ozone_wind, and the second argument is our data for prediction, in this case wind_data. So we execute line 13, and on line 14, I specify wind_data so we can see the results in the console. So what we get in the console for our values of wind 7, 10, and 12 are the predictions 58, 41, and 30. So on our plot at about 7 miles per hour of wind, we get a point that's on the line that goes through the plot. So the line that's defined by our model. And 41 at 10, and then at about 12, we have around 30, so 30.26. So these all fall within the range of values that we had from our data set. But what happens if we look at data outside of that range? So on line 16, I have another variable, wind_data2, is assigned to data.frame with wind assigned to the vector of values created by C with the values 0, 2, and 4, and 17, 20, and 22. So I'm looking at the very extremes of the wind values to see where my model is deficient. So I'll execute that line and create our wind data 2. And then on 19, on wind_data 2, I create another column called ozone prediction, and then I assign that to the predict function with ozone wind and wind data 2 as arguments. So I'll execute that, and then on line 20, I'll display the wind_data2 data frame. And in the results, there's a few things that we should be aware of. Well, the first value with wind 0 gives us a value of 96.87, and the values above 17, so the values of wind at 20 and 22, are predicted to be negative values. So that's hugely problematic because we can't have ozone, the amount of ozone, anything less than 0. So that would have to be corrected if we were going to improve this model. Now, the wind speed of 0 is a problem because the value is 96.87. And if I output by calling max of air $ozone, now what we get for the maximum ozone in this dataset is 168. But with a wind speed of 0, the maximum we can get from this model is 96.87, which is a huge discrepancy. So everything above 96.8 will never be predicted, and there are quite a few values in that data set, especially below a wind speed of about 6. There are quite a few values around 100 or greater. So the predict method is good when our model is good, but it also helps us recognize where our model doesn't fit. So we don't always have to use it on a good model. We can use it on a deficient model to highlight and explain those deficiencies. And that concludes this demonstration of using prediction on a linear model. In this video, I'll present how to perform preparatory steps needed before creating a logistic model. Now for the logistic model, we're talking about a response that is binomial. So this will be a binary outcome of 0 or 1, but it could be true or false, yes or no, or on or off. Now in the example code, I first bring in the dplyr library. So I call library of dplyr, and then on line 2, I call library of tibble. So we'll get those libraries loaded, and then we can look at the data set we're going to be using for this example. So I'm going to be using the built-in dataset mtcars. So before we get started, I'm going to call help on mtcars. So in the help section of RStudio, we have the motor trend car road tests. So this is the information about 32 cars from that era from 1973 and 74. Now if I scroll down to the format, it tells me I have a data frame with 32 observations on 11 variables. Now we're not going to be using all 11, but what we're going to be doing is taking the horsepower, the HP, the displacement, disp, and the weight, WT, and use that information to predict whether the car's engine is a V or straight engine. So the VS column has a 0 if the car has a V engine like a V8, or the column will contain 1 if it's a straight engine. So let's have a brief glimpse of the data set. So on line 5 of my example code, I call a glimpse of mtcars. And in the console, I get some information about the car's data set. So we have observation 32 and variables 11. So if I look through the output, we have the HP. So there's values like 110, 93, 175, 105. So there's a bunch of different values. The weight is in thousands of pounds, so 2.62, 2.875, etc. And the VS column we're going to be using has 00110, so it's all ones and zeros. So it is a binary response. So that's what we're going to be predicting. So for that, we need a logistic model. Now let's check before we continue whether or not the dataset has any NA values. So if it does, we want to filter these out. So on line 7, I call any NA of mtcars, and that returns false. So we don't need to worry about NA values with this data set. Now I'm going to perform a small transformation of the data. So I'm going to create a new data set, a new data frame called pcars. So here on line 9, I have pcars, and I assign that to the function row names to column, which I get from the tibble library. I give it mtcars and var equals the character string car. So in the mtcars data set, each row of the data frame is named by the car name, make, and model. But I want to convert that to an actual column. So I can convert the row name, which contains the car, to a column. And I'm going to call that column car. So that's what this method does. And then I pipe that into a select that comes from dplyr, and I give it the car, the VS, the HP, the disp, and the WT for weight. So what we do is extract a subset of the data set and perform a small transformation so that we have the information we'd like to be working with and nothing else. So I create pcars and then output it just to see what we get in the console. So we have all of the cars. We have the car, the VS, the HP, the disp, and the weight of all 32 cars. And now on line 13, I set a random seed because I want to sample a subset of this data to train our model and then keep the remaining values, the remaining records, to test the prediction capabilities of our data set. But I want that sample to be predictable, so I set a particular seed number so we get the same sample every time we run it until we change the seed. So on line 13, I do set.seed with the number 111. And now on line 14, I take a subset of my pcars data frame, and I'm going to take this subset for training our model. And I'm going to call this training set pcars_training, and I assign that to pcars piped into the dplyr function sample_n with 25. So we're going to train it with 25 records of the dataset, and we're going to save the remaining 7 for testing our model. So the test set on line 15 is pcars_test, and I assign that to pcars, but with the setDiff, so the setDiff method coming from the dplyr library with the pcars training. So setDifference will remove or keep all of the elements or records of pcars but excluding anything that appears in PCAR's training. So now we've extracted our data, we've separated it into training and test, and we're ready to perform a logistic regression. And that'll be covered in the video titled Using GLM. And that concludes this presentation on logistic data preparation. In this video, I'll demonstrate how to apply the GLM method on a logistic regression problem. So in this example code, I've already run the first 7 lines of code, which came from the video titled Logistic Data Preparation. So now we have our training set that we're going to use to create a model using the GLM method for generalized linear model. So in this case, GLM is performing a binomial logistic regression, which is what we specify as the family. So this gives us 2 possible outcomes, 0 or 1, as opposed to a multinomial logistic regression where we can have more than 2 outcomes. So on line 9, I have pcars_model. So this is going to contain the result of the model, and that's assigned to GLM, and we specify the formula. So VS is a function of the weight, WT, plus HP, the horsepower, plus disp, the displacement. And our data comes from the training set. So pcars_training, and family equals binomial. So I'll execute this code to create our model. Now that we have our model, we can use it to make predictions. So on line 13, I have pcars_test, and in square brackets, I have the character string predicted. So in our test data set, we have the values we're going to use for prediction, but I'm also going to add a new column called predicted, so we can see if the predicted values match up with the actual values. So this is assigned to the if-else statement. So we're using if-else to discretize the results. So there will be 2 possible values in the result, but we need to decide whether they're assigned to 1 or 0. And the if-else takes the predict method, which takes the pcars_model and pcars_test. So the model was created with the training set, but now we're going to validate the model using the test set. And anywhere this predict function returns greater than 0, we encode it as 1 or a straight engine. Otherwise, we encode it as 0, which would be a V engine. So I'll execute line 13 and 14. And now we can have a look at the results. So pcars_test contains the results, and I've printed them to the console. So we have our list of cars, the actual V or straight engine categorization 0 or 1 that comes from the MT cars dataset, the horsepower HP, the displacement, and the weight. So if we look at the first car, the Duster 360, it's a V engine, and the predicted outcome is also a V engine. So the zeros match up. The Mercedes 230 was predicted to be a straight engine, and then the actual is a straight engine. So all of the predictions that we have in the results seem to match up except for one. And that's the Porsche 914. So that's the 6th record in the prediction set. So it's encoded as a V engine, so 0 with horsepower of 91, displacement of 120.3, and the weight of 2.140. But we predicted it to be a straight engine. Now, this car is a bit of an oddity in this data set. It's neither a straight engine nor a V engine. It's actually a flat engine with opposing cylinders. So it's not surprising that there's an error in our model when it comes to that particular car. Now, we're also working with a small set. We only have 25 cars that we're training with, and we're only trying to apply the prediction to 7 different cars. We've predicted them correctly, but we're only dealing with a small sample size. If we wanted to improve our model, or to make it more comprehensive, we'd need a much bigger training set and test set to actually validate the results fully. But this is how we go about carrying out a logistic regression using the GLM method in R. And that concludes this demonstration of using GLM. In this exercise, you'll load a dataset appropriate for a linear regression analysis. Then plot the linear relationship from your dataset for the dependent and independent variables, or the predictor and response. Then create the linear model, and finally use the predict method on the linear model. Now pause the video and perform the exercise, and when you've completed it, come back to the video to see what I did. So the dataset I'm using is the cars dataset. So I'm going to run help of cars on line 1 so we can see the dataset we're going to be using. Now this is a built-in dataset that comes with R, and it's the speed and stopping distances of cars. So this comes from data recorded in the 1920s. So this data frame has 50 observations on 2 variables. So the variables are speed, so how fast the car is moving in miles per hour, and the distance, or the distance it takes to stop the car in feet. So if you're traveling at 15 miles per hour, how long does it take the car to stop? So the first thing we'll do is check to see if there are any NA values in the dataset. So on line 2, I execute any NA of cars, and it returns false. So there are no NA values that we need to deal with. And now on line 3, I'll do a glimpse of cars, so we can see the structure of it in the output. So in the console, I have observations 50 and variables 2, and the speed is encoded as a double. So it starts with values of 4s and 7s, and so it builds up the number of speed values and the corresponding distances, so dist, which is also a double. Now let's create our model. So on line 5, I've called this model stopping underscore model, and I assign that to LM, so linear model, of the dist tilde speed. So it's the stopping distance as a function of the speed of the car. And I specify the car's dataset. So I'll create the model, and now I'll plot the relationship. So on line 6, I have plot, dist, tilde speed, comma, cars. So we have our relationship in a plot. So we have speed along the horizontal axis and distance on the vertical axis, and we have a scatter plot of all the different points from the data set. So each observation is plotted. Now we'll draw an AB line, a horizontal line through the mean of the stopping distance. So we can see what the average stopping distance based on the entire data set. And now in line 8, I'm going to do an AB line of the stopping model. So now we have a line drawn on our plot representing our stopping model. So it's a line that tries to best fit the speed distance plot that we have. Now I'll create a test set of speeds that we're going to use to predict the stopping distance. So on line 10, I have test underscore speeds is assigned to data.frame with the variable speed, which is assigned to the vector created by the function c with the values 5, 10, 15, 20, and 25. So we're going to consider cars traveling at 5 miles per hour, 10 miles per hour, 15 miles per hour, 20 miles per hour, and 25 miles per hour, and see what the typical stopping distance or the predicted stopping distance we'd have based on this model for those given speeds. So I create that data frame, and now I'm going to add a new column to the data frame called dist. So this test speeds only has the speed column, and I'm going to add a column with the string dist. So test speeds indexed by dist is assigned to predict, where we pass the stopping model and the test speeds. So now we've created our predictions, and we can output test speeds to see what they were. So we have our test speeds, which has a speed column with our 5, 10, 15, 20, and 25, and the corresponding stopping distances. So at 5 miles per hour, it'll take typically 2.08 feet to stop. At 10 miles per hour, it takes about 21 feet to stop. At 15, it takes 41. At 20 miles per hour, it takes 61 feet to stop. And at 25 miles per hour, our model predicts that it will take 80 feet to stop. And that concludes this exercise on creating a linear model.